All right, so today we are doing theoretical versus empirical probability. Okay, your essential question is, can you determine if a simulation is consistent with a theoretical probability? Okay, that is your essential question today. Can you do it? Can I determine if a simulation is consistent with the theoretical probability? Okay, well, it would be nice to know what that is. So, we have actually been doing theoretical probability this whole time, where we have the number of outcomes in a certain event over the number of outcomes that are possible in the sample space. Okay, like flipping a coin. There's one heads, there are two sides, so it's 1 out of 2, 0.5. Okay, that is what we have been doing, calling theoretical probability. So we do the division. It comes from sample spaces of equally likely outcomes. So like rolling the dice, flipping a coin, picking a card out of a deck of cards and putting it back, spinning a spinner. Okay? All of those come from theoretical probabilities. Okay? Essentially what we're doing is we're finding what should happen. If I flip 20 coins, I should get 10 heads, 10 tails. Is that true? No, not. I cannot actually predict what is going to happen. I just know that's what should happen. Okay? So we're going to compare today what should happen versus what actually does. So theoretical probability of an event is the number of ways the event can occur divided by the total number of outcomes. It comes from a sample space of equally likely outcomes, flipping a coin, rolling a fair die, etc. Give you about 10 seconds. Ten, 5, 2, 1. All right. There is another way to estimate probability. That is called empirical probability. Okay. The empirical probability of an event is determined by the proportion of times the event will occur in a long series of independent trials. Okay. So, we're back to tossing our coins. So we know my probability of what should happen is 0.5. Empirical is going to be the probability that actually happened. So when I tossed my coin 10 times and got 8 heads, what's the probability there? 0.8. Okay? And then when I flipped the coin 10,000 times, I got 5,020 heads. That probability is 0.502. What do you notice about the different times I flipped my coin? Okay, because the more you do it, the closer we're going to get to theoretical. I like it, because out of those 10 times I got 8 heads. That's nowhere near my half and half, right? But I got really close to being half and half with 10,000 flips. Okay, so that's actually a theory. That's actually it's a law. Started off as a theory, it became a law. I'll give you a second. What that law is? Give you 10 seconds. I know it's a lot of writing today. Yeah. This is probability. We're doing statistics next. This is in the field of statistics. Yeah, I would put it in the bubble. Nope. Oh, sorry. So according to the law of large numbers, as the sample size increases, the empirical probability will approach the theoretical probability. So, like Colin just noticed, the more times we flip the coin, the closer it got to what it should be. The law of large numbers. The more you do it, the better. It starts to kind of balance out. All right, I got a fun little video for you.
How does an insurance company decide how much to charge for car insurance? How do casinos set up payout structures to make sure that they make a profit? How does a poker player decide whether or not to fold? How do we efficiently measure the appeal of a political candidate? The answers to these questions are informed by the law of large numbers. The law of large numbers states that as the number of trials or observations increases, the actual or observed probability approaches the theoretical or expected probability. This is important to understand because it allows us to predict and have confidence in how events will play out in the long run. Let's take a common example, flipping a coin. Assuming the coin is fair, we know that the theoretical probability of flipping heads is 0.5 or 50%. However, that doesn't guarantee that if we flip a coin 10 times, we'll get 5 heads. But we can be confident that as we continue flipping a coin indefinitely, the cumulative proportion of heads flipped should get closer and closer to 50%. Looking at this graphically helps to illustrate the concept. I just flipped a coin 20 times and these are the results. After each flip, we'll calculate the cumulative proportion of heads so far. So the first flip is tails. So our current proportion is 0 heads out of 1 flip, 0%. The second flip is also tails, so now it's 0 heads out of 2 flips, still 0% heads. Next flip is tails again, 0%. Then heads, now we have 1 heads out of 4 flips, 25% heads. Flip again and it's heads, 40%. Heads again, and we finally hit our theoretical probability of 50% for the first time. Let's keep going. This graph shows the observed probability approaching the theoretical probability. One common misconception, referred to as the gambler's fallacy, is that if the first 4 flips were tails, you're more likely to get heads on the next flip because the proportion is supposed to even out to 50% heads. This is not the case because each flip of a coin is an independent event. Its outcome is unaffected by all previous events. So if you start out with 4 tails in a row, it's not that you're more likely to get heads. It's just that in the grand scheme of things, 4 tails flips will get averaged with a huge number of flips that are expected to yield an even number of heads and tails, causing the proportion to approach 50% as the number of trials increases. Another version of the law of large numbers explains that the more people from a population that you sample, so the larger your sample size, assuming your sample is free from bias, the closer your sample average will be to the population average. Let's say you have a group of 100 people. Each has some number of dollars in their wallet. We ask one person how much money she has in her wallet, we'll get our first observation, $49, which might be pretty far from the average of the group. After asking the second person, $29, and averaging that value with the first, we are likely to have a better estimate of the group average. As we continue this process of adding observations and thereby increasing our sample size, we'll generally get better and better estimates of the group's average. So the law of large numbers gives us a compass with which to navigate the randomness around us. Even though we can never predict the outcome of a single coin flip, we can know that over time about half of the flips will be heads. And in general, the principle supports the idea that a well-founded strategy that is followed consistently should win out over time, even though it might result in a few negative events along the way. Thanks for watching. See you next time.
All right. So it gave you a little bit more of an understanding of the law of large numbers. So let's work with it. Alright, so we have Jamie and Marcus. They are rolling 2 dice 30 times. Okay? The sum of their rolls are shown below. So they have 2 dice, meaning they're going to add up their totals. Dice 1 and dice 2. Okay? What is the empirical probability of rolling a sum of 6? So is that what should happen or what did happen? That is what did happen. So they rolled the dice 30 times and they got how many sums of 6s?
1, 2, 3, 4, 5, 6.
Yes. Which simplifies to 1/5, which gives us 0.2. All right. The theoretical probability is what should have happened. Remember, we have 2 dice. We got dice 1. We got dice 2. They're 6-sided die. What are combinations that add up to 6?
2 and 3.
2 and 4 add up to give you 6. 1 and 5.
3 and 3.
3 and 3. 4 and 2. 5 and 1. Right? So how many combinations are there to get a sum of 6? There are 5 possible ways to get it out of how many total combinations? 36. Good. They each have 6 sides. So what should happen is 5 out of 36, which is about 0.139. Okay? So how can we compare the two? What do you notice? Are they the same? Are they close? Is one bigger than the other? They're kind of close. Looks like what should have happened, though, what did happen was more. Yeah? Do we think we had a law of large numbers going on? No, my sample size is actually smaller than the original sample size, isn't it? There were 36 total combinations, and they only rolled the dice 30 times. So they actually went the opposite direction. They did smaller sample size. So the empirical probability will get closer when more dice are being rolled. Currently, with only 30 rolls, though, the empirical rule is larger. The empirical probability is larger than the theoretical probability. So there was not enough rolls for this one. Not enough rolls. We got about 3 more examples, and then I'll let you work on your stuff. We have a spinner, we have groups, and we have one more dice one. You good? All right. We have Karen. Karen is spinning a prize wheel. It is divided into 3 equal sections. The first is a free t-shirt. Second is a pencil. The third is spin again. She spins the wheel 15 times, and we see her results. Okay? What is the theoretical probability of spinning the wheel and winning a pencil? Is that what should happen or what did happen? Theoretically, it should happen. So how many total options does she have? 3, and how many of those is getting a pencil? Just one. So it's 1 out of 3, which is 0.3. So 1 out of 3 options. Have y'all noticed like that, like Dave and Buster's or any of those like game places, if you have a wheel, if like the bigger ticket spots are smaller, like your 1,000 tickets is like a sliver, but then like your 5 tickets is like half the wheel. Sneaky, sneaky. It's not fair. All right. So that's what should happen. Now let's see empirically what did happen. So how many spins did she take? She took 15 spins, and how many of those spins did she get a pencil? 4. 4 of those 15 spins resulted in her winning a pencil. Okay, so 4 over 15 simplifies to 0.267. Okay. Were these closer to each other? Yes. With what actually happened, was that sample size bigger than the original? Yeah, it was like 5 times as big, right? Only 3 combinations, she spun it 15 times. So her sample size was getting bigger, so the more and more that she spins, hopefully the closer and closer she'll get to the 0.3. Huh? No, just the wheel in general. The wheel had 3 sections, and one of them was a pencil. Yep. And then what she actually did, she actually got 4 pencils when she spun the wheel 15 times. Yeah. So this one was closer because our sample size was getting bigger. My amount of spins. Alright, think about this one. You assign 3 different groups to flip a coin repeatedly. Group A is going to flip the coin 50 times. Group B is going to flip the coin 200 times. And Group C is going to flip the coin 400 times. So which group is likely to have results that are farthest away from theoretical probability? Group A? Why are you telling me Group A? Because it's the smallest one. Good, that's what we just saw in our last 2 examples. The smaller the sample size, the further away we were. Okay, so Group A will probably be the farthest away from our theoretical probability. All right, one more. Rolling a dice again. All right, so you are rolling a dice. You rolled it 15 times. This is what happened. You got 1 1, you got 2 2s, you got 6 3s, 1 4, 2 5s, and 3 6s. Okay, frequency shows how often something occurs. Okay, does this represent the theoretical probability of rolling a dice? Why or why not? All right, well, what is the theoretical probability? They all be 1 out of 6, right? Because there are 6 sides. Ignore this. There are 6 sides, so theoretically we have a 1 out of 6 chance for each of them. So 0.167. All right, what actually happened? So how many times out of their, so these were all out of 15 rolls, right? 15. So out of my 15 rolls, how many times did I roll a 1? 1 time. How about rolling a 2? 2 times. Rolling a 3? 6 times. Rolling a 4? Rolling a 5? 2. Rolling a 6? 3. So that actually gives me 0.06, 0.13, 0.4, 0.06, 0.13, and 0.2. So, did they show me theoretical? Is what they did, does that represent the theoretical probability well? No. So is 15 rolls enough? No. They are all over the place. So it does not represent theoretical probability. We need to roll the dice more so we can get closer to it. We good? Great. You okay? Oh, okay. Ooh, did it work? Did it work? Did he scare them away from you? All right, you're going to work on your worksheet that I gave you during the video. If you get done, get stamps and turn it in. We will review tomorrow. We will test on Friday.